Hello, my name is John Moyer, and I want to welcome you to the NIH Office of Disease Prevention's Mind the Gap webinar series. This series explores research design, measurement, intervention, data analysis, and other methods of interest to prevention science. Our goal is to engage the prevention research community in thought-provoking discussions to promote the use of the best available methods and to support the development of better methods. Before we begin, I have some housekeeping items. You can submit questions during the webinar via the chat pod. You'll need to open the pod by clicking on the chat icon located in the lower right-hand corner of your WebEx window. Please direct your questions to all panelists. We will open the floor to questions that have been submitted via WebEx at the conclusion of the day's talk. The slides and video recording will be posted on our website, prevention.nih.gov/mindthegap, in approximately 2 weeks. You will receive an email when they are available. Lastly, we would appreciate your feedback about today's webinar. Upon closing the WebEx meeting, you will be prompted to complete an evaluation. We would appreciate your feedback as it will help us improve this webinar series. At this time, I'd like to introduce Dr. David M. Murray, Associate Director for Prevention and Director of the Office of Disease Prevention.
Thank you, John. I'm very happy to introduce Donald Hedeker, who's our speaker today. He is Professor of Biostatistics in the Department of Public Health Sciences at the University of Chicago. His chief expertise is in the development of statistical methods for clustered and longitudinal data, with particular emphasis on mixed effects models. With Robert Givens, Dr. Hedeker is the author of the text Longitudinal Data Analysis, published by Wiley in 2006. More recently, he has developed methods and software for analysis of intensive longitudinal data, which are data with many measurements over time, often collected using mobile devices or the internet. Such data are increasingly obtained by researchers in many different areas, such as mobile health and ecological momentary assessment studies. In 2000, Dr. Hedeker was named a Fellow of the American Statistical Association, and he became an elected member of the International Statistical Institute in 2015. Also in 2015, he received a Long-Term Excellence Award from the Health Policy section of the American Statistical Association. In 2016, he was elected to the Society for Multivariate Experimental Psychology. Dr. Hedeker has served as an associate editor for Statistics in Medicine since 2006. It is my very great pleasure to welcome Dr. Hedeker.
Well, thanks very much, David, and thanks, John, for this opportunity to talk about these extended kinds of multi-level models. So today we're going to go over cross-classified, multi-membership, and then dynamic group multi-level models. So here gives an outline to the slides that I'm going to go through. And incidentally, I'm going to put in the chat a web location where you can actually get the slides and the materials, data sets, and syntax files. You can get them right now. And so feel free to obtain those things. So we're going to talk first about cross-sectional clustered data, give a little introduction about multi-level, then get into the cross-classified multi-level models, and then the multiple membership multi-level models. Then we're also going to turn our attention to where we have longitudinal and clustered data and focus there on two classes of models, one known as acute effects cross-classified multi-level models, and then also the dynamic group multi-level models. So that's the what we're going to be going through. I have several references throughout the PDFs, and so all of those are listed on slides 48 and 49. In the slides that I'm going to go over, I'll primarily focus on SAS implementation of these models, but I also have an appendix with implementation, how to do this with SPSS and Stata as well. Okay, so what are multi-level data? These are data that are typically hierarchically structured, nested, clustered, and you often get data from units organized or observed within units at a higher level. That's the two-level scenario. So you might have students within classrooms, siblings within families, and then it also pertains to longitudinal, where you have repeated observations nested within individuals. And these are the two-level data structures. At level 1, you have your primary outcome variable, you have some other variables. Level 2, you have typically the context, the cluster, and you'll have some variables there. and you want to acknowledge that cluster in the analysis. That's the idea in multi-level data analysis. Why do we do this? We want to, first of all, find out how much variability is there, say, at the classroom level, at the student level. We want to have a model that allows covariates at both of those levels, and then potentially interactions, cross-level interactions. From a statistical point of view, the reason to do multi-level data analysis is because the observations are not independent, and therefore the inference from a model that would assume independence is not quite correct, leads to type 1 error. So students within classrooms, they share influencing factors. We want to acknowledge that in our model. So really, multi-level data analysis is another example of what I think of as the golden rule of statistics. One person's error term is another person's career, right? Or many person's career. It's certainly been my career. Now, what are cross-classified multi-level data? So here we have subjects classified by, say, 2 or more types of clustered, but they're not necessarily hierarchical or nested within each other. So we could have students who are clustered within schools and neighborhoods, but the students from the same neighborhoods might go to different schools. So it's not a hierarchical setup. Or in the medical context, we might have patients who are clustered within providers and hospitals, but again, they might be seen by the same provider at potentially different hospitals. So again, it's not strictly clustered and hierarchical. So this gives a schematic of what the difference between a nested and a cross-clustered. So here in this top line, you can see that all the kids, and here the X's would be the observations, all the kids in school 1 reside in neighborhood 1. All the kids in school 2 reside in neighborhood 1, et cetera, for 3 and 4, right? So this would be where students are nested within schools within neighborhoods, and it's strictly hierarchical. Here shows a clustered scenario, cross scenario. Now here you can see that all the kids in school 1, they're from different neighborhoods. Likewise in school 3 and 4. Now it doesn't have to be that all the schools are that way. So school 2, they're only from neighborhood 1, but you can see there's several schools in which there is this crossing of these 2 kinds of clusters, the schools and the neighborhoods. And so what we're interested here is to assess how much variability here is attributable to these 2 kinds of clusters, schools and neighborhoods, how much influence they have on the outcomes from the students. Okay. So here's the first example we'll go through for the cross-classified multi-level models. And I want to point out at the University of Bristol, they have an excellent site for multi-level resources, and that's where I pulled these data from. And this is from a data set that was collected from children in Scotland in which they attended primary schools and secondary schools. And again, these were not strictly hierarchical. So was the case that some kids from the same primary school went to different secondary schools. Okay. The outcome we're going to look at is the attainment score of the students at age 16. And the 2 kinds of clustering that we're going to consider is the primary school. And so we have the ID there. And then also the secondary school, and we have the ID for that as well. And then there's some additional covariates that we might consider in our analysis. Most of these are collected at the student level, though some of them could certainly be at either of these 2 kinds of clusterings. This shows an Excel file. Again, this is in the materials that I've made available, so you can actually do these analyses. Here the data are sorted by the primary school ID. You can see that's the PID variable. So everyone here is in the first primary school, but they're not sorted by secondary school ID. Okay? Most of the software doesn't really need the sorting. They can figure it out. So no concern there. And here's our attainment score that we're going to be modeling the dependent variable. Okay? Now, luckily, in both SAS and SPSS2, they make it very easy to do these cross-classified models these days. With Stata, it's a little bit more work involved. That's in the appendix, but also very doable. So here shows a null model first, in which I'm using in SAS proc mix. Now in SAS, because uppercase, lowercase does not matter, what I tend to do is to use uppercase for SAS specific syntax and then mixed or lowercase for things that I can name. So hopefully that helps in the understanding. So here I have proc mixed. I indicate the data set in in here. Cove test will then provide testing of the covariance parameters, so it's a useful option. On the class statement, I identify my two cluster ID variables. Okay? And here in this null model, I'm just going to model the attainment score in terms of no covariance. S here stands for solution. That will just print out the, in this case, the intercept. Okay? And then on the random statement, all I need to is include those two kinds of ID clusterings, the primary school and the secondary school. Okay, so it's very simple. Okay? Here shows if I add in covariates in SAS, it's just adding in things after the equal sign on the model statement. So that's very simple to do as well. So you can see here for cross-classified analysis, it's really a very simple adjustment to a hierarchical kind of modeling. And here shows what we'll get from this null model first in SAS. So the dependent variable here is attainment. It's using restricted maximum likelihood by default. It identifies there's 148 primary schools. There's 19 secondary schools. The values are just the ID sequential numbers from 1 to 148 for primary, 1 to 19 for secondary schools. Okay, so it does takes care of things for us. Okay, there's this many students, 3,435. Here show my covariance parameter estimates. Estimates, standard errors, z-values, p-values. So we see that the primary school variance, so the heterogeneity attributable to primary schools seems to be much larger than that doing for secondary schools. Okay, and here shows the fit statistics and then finally my intercept. Now what I want to also show from this model, this cross-classified model, is how we can calculate intra-class correlations here for how much variability is attributable to the primary schools and how much variability is attributable to the secondary schools. Okay, so this shows it here. I'm listing just these variance estimates that I got from this first run. So students from the same primary school but different secondary schools, the ICC there would put in the numerator the school variance, primary school variance, and then the denominator would put the sum of all three variances: the residual variance, the primary school variance, the secondary school variance. And so I get an ICC of about 12% here. So students from the same primary school are correlated a fair amount. Now, what about secondary school? But students who are from the same secondary school but different primary schools, numerator would have the secondary school variance in the numerator. We do the calculation, we find out about 4% of the variance is at the secondary school level itself. Okay? Now, there are some students who went to the same primary and secondary schools here. For those, the ICC would put in the numerator both of the school variances, and we get an ICC here in this null model of about 16%. Okay, so you can see that the amount of variability attributable to both of these schools is rather considerable here in this null model. Of course, as we add in covariates that explain some of this variation, these ICCs would presumably go down. Okay, now here's an additional twist in cross-random effects models that's kind of interesting sometimes. We can actually have interactions between these two kinds of clustering. And the idea here is that it could be the case that some secondary schools, say, might benefit students from particular primary schools more so than other primary schools. So there's an interaction that could be going on. So it would relax the assumption of additive random effects. And this is something worthy of checking out, I think, when you have these cross-classified models to see if this is present or not. And I'll show how to do that. Now, we do need duplications in order to do this. So here I put a situation where there's singletons only. In other words, there's only one student with the crossing of secondary school 1 and primary school 1, et cetera, et cetera. So in this table here, you can see there's no duplicates for the cells, and in that case, you could not estimate an interaction. Okay? However, in the most cases, you would have some duplication where there's more than one student in this crossing of these, say, primary school 1 and secondary school 1, et cetera, et cetera. And in that case, this possibility exists. And again, it's worthy of checking out. Let me show you how to do that. Quite simple. All we do is on the random statement, just indicate a product term for the primary school ID, the secondary school ID. Okay, and this relaxes the notion of an additive effect of these two kinds of clusters. Let's see if it makes a difference here for this data. Okay. So here, when we do that, we get an additional covariance parameter. That's the product term here. We see numerically, it's 0.23. By the wall test, it's not quite significant. What I'm going to also do is a likelihood ratio test. Okay. And so here I'll take my residual log likelihood and compare it to what I had in the previous model that did not have this interaction term to help guide me whether this should be included or not. Okay. So the model, assuming no interaction, had this deviance here with this, and -2 times the log likelihood is what's sometimes referred to as a deviance statistic. You can see that they don't differ by much, and the resulting chi-square statistic is like 1. Okay, so there's no interaction effect on the clustering here. The additive model would be reasonable in this case. Again, something to check to help guide which of these two kinds of cross-classified models seems the one to go with. Now here, let's say the model with the random effect interaction that you want to go with that model. I'm just illustrating here how we would now calculate the interclass correlations. Here again, this is with the null model with no covariates. So students from the same primary school, it's the same logic. We put the primary school variance in the numerator. We put all of the variance parameters estimates in the denominator. We get an ICC of about 10%. Secondary school, same idea, secondary school variance in the numerator. Here we get an ICC of about 4%, 3.5%. Now, if they went to the same primary and secondary schools, here's where we add in this interaction, the interaction between these two kinds of clusterings. And so now the ICC here is 15.5%. Okay, so if you do have this interaction of the two random effect clusters in your analysis, this is how we can calculate the ICCs. Okay. This just shows the equations. I know many of you want to see the equations, right? Show me the equations, right? So this just shows the equations here for the model with additive random effects. Okay, so here in terms of the notation, I have students K nested within the crossing of primary schools I and secondary schools J. Okay, so we have covariates here in the model. They could be at any of these three levels, and they could be cross-level interactions. And then we have these two clusters, and they each have their own specific variance parameters, as does the residual variance. And then when we add in the interaction, we have an additional variance parameter, the crossing, or sorry, the interaction of primary and secondary schools in this case. Okay, so what you can hopefully glean here, it's really not hard to use the current software to estimate these kind of cross random effect models, and SAS makes it quite simple to do it. Okay. Now, let me talk to multi-membership models. These are kind of interesting, I think. Here, you get subjects nested within more than one cluster. Okay? So in the educational context, you might have students who are seen by more than one teacher, right? So let's say they have different periods in their day. They go to see different teachers, and you want to know what is the clustering of the teacher on the student. Okay? But students aren't within just the same teacher, they're within different teachers. Or in the health context, we might have patients who are seen by more than one providers. Again, I think these examples are pretty common. I don't know that people always analyze it doing so, but I'll show you how to do that so that you can take advantage of this. Now, what you need to do here with multi-membership models is you kind of need to know how much is the student seen by these multiple teachers. So we need to have weights that represent the degree of the membership for a student to all the different teachers, all the different providers, something like that. Okay? And the sum of these weights equal 1. Okay? They represent amount of time or the degree of membership of the student, let's say, in the cluster. Okay? Now, you can imagine that there might be a few different ways to define these weights. And so what you might want to do in that case is to do sensitivity analysis to see how the choice of these weights, how that might affect the results or not. Okay. So here shows the idea again in a just brief schematic. Let's say we had a hierarchical structure where student 1 was only seen by teacher 1, student 2 only by 2, 3, 4. Okay. Each student's nested within only one teacher. Okay. But it could be the case, as I mentioned, that students are seen by multiple teachers. So this first student, for example, is seen by all 4 and spends a quarter of their time with each of the 4 teachers. The next student is only seen by 1. The third student is seen by 3. The fourth student is seen by 2. Okay. All right, so these numbers here are going to be the weights, and you can see they sum to 1, and they represent, again, the degree of membership of the student in the different clusters. Okay. Now here I went to Bristol again, the UK site there, and I got a data set. They simulated that from 1,000 patients who were treated by 25 nurses. 400 of these patients were treated by only 1 nurse, 300 were treated by 2 nurses, 200 by 3 nurses, 100 by 4 nurses. Now what you're going to see with these multi-membership models, the models themselves are not really that difficult to run, but there is a bit of data management that needs to be done to do them. Okay. So here I have a patient ID. I have the outcome variable, which will be their post-operation satisfaction. There's a covariate at the patient level. What was their assessment prior to the operation? Okay. And then this is a variable that indicates how many nurses were seen by the patient. And in the simulated data, they were seen by 1 to 4. Now, then I've got IDs for these 4 nurses that the person was seen by. And then I've got the weights. P1 to P25, which is the amount of time, the proportion of time that each patient spent with each of these 25 nurses. Now, additionally, what we're going to do here is to have a covariate at the nurse level, their job happiness score. So then in the data set, there's 25 columns, H1 to H25, which represents the happiness score for nurses 1 to 25. And I'm going to show how we can include that in the analysis. Okay, so this is a data set. Each line represents each patient, and we need here to know the proportion of time each patient spent with each of these 25 nurses in this case. Okay. So this is what the Excel file looks like. Patient here, you can see that's the first ID. Okay. And then notice here in this first slide, this person here, patient 11, P1 to P25, they have a 1 for P1. So that person was seen by the first nurse only. Okay. And so all the other P variables here equal 0. Okay. So that was the person seen by only 1 nurse. Okay. Now, if you go further in the data set, you'll see here, for example, patient 403, they were seen by 2 nurses. One of the nurses, they were seen a little bit over half the time, and the other nurse a little bit under half the time. Okay. And you see similar patients that were seen by 3 or 4. Okay. So these weights are very important. Okay. Okay, now here shows that covariate that's at the nurse level, those fields. Okay, so that's job happiness value. And so I need to have those as separate variables for each of the 25 nurses. Okay, so H1 to H25. So within a column, it's the same value because it's the satisfaction rating here for the first nurse. Okay. Across columns, it changes, right? Because it represents the happiness here for the second nurse, the third nurse, et cetera, et cetera. Okay, okay, so we're going to see how to include this job happiness of the nurse in the analysis as a covariate. Okay, so here shows my SAS syntax file. I read in this Excel file. Whenever I read in a data set, I typically run proc means to see what it looks like. Now here's this little bit of management that I'm going to use to provide for me a weighting of the nurse happiness values by the proportion of time the patient spent with that particular nurse. and that will form a happiness weighted sum, you can think of it as, that's going to be my covariate in analysis. Okay, so it's not difficult to think of. What we're doing is to weight each of these happiness scores for the 25 nurses by the proportion of time the patient spent with that particular nurse to form my happiness covariate that I'm going to include in the analysis. Okay? Now, the other thing that we're going to need to do is we're going to need to consider all of these patients as nested within the big data set. So I'm creating a variable here I call cons is equal to 1. We'll see how I'm going to utilize in that syntax. Okay, so here first I'm going to run a null model. So let me show you how a multi-membership model looks like. Here I identify that variable, the constant, is equal to 1 on the class statement. And I basically indicate that all of the subjects are nested within that variable, meaning they're all nested within the one data set. However, what I'm also doing here is to indicate those weight variables, 1 to 25, they're all random effects. So there's 25 random effects in this model. Can you believe that? Blows your mind, right? However, type equals Toeplitz 1, what that syntax tells SAS is that all of these random effects essentially have the same variance. Okay? That's the nurse variance. That's the cluster variance. Okay, and they're uncorrelated. Okay, so that's what's going to tell SAS basically there's only one variance. It's the nurse variance, right? The cluster variance. However, the P1 to P25 indicates how much time each patient spent with each of the 25 nurses. Okay, so this is how to do the null model for a multi-membership model. Again, the critical thing here is to have those weights. Okay? And then you just indicate that everybody, all the patients are clustered within the one data set, and type equals Toeplitz 1 is the structure we want. Okay? Now, here I'm putting in the patient's assessment as a covariate. And then here I'm also putting in the happiness, the weighted average that I calculated as a covariate. Okay. All right, so this is how to do the multi-membership models. Again, it takes a little bit of data management, but I think the actual syntax for running it here with SAS is rather straightforward once you get the hang of it. Okay. Let's look what the output looks like here. Okay, so here I'm going to show the output for the model with the two covariates. Here, notice it indicates cons has one level, one value, right? So it's including everybody basically within the one cluster, as it were. However, within that one cluster, there's 25 random effects. Those are the weights. Okay. So here it identifies that there's one subject. That's kind of a misnomer in a sense, right? There's really 1,000 subjects here, right? So that's the max obs per subject. That's the 1,000 subjects. And the columns in Z, that's how many nurses there are. Okay, because what we're kind of doing here is tricking a hierarchical software to do this multi-membership model in this way. Okay? And so here the variance for the constant, that's the nurse variance. Okay? You can see it's rather large. Here's the residual variance. Again, we'll calculate an ICC in a minute. Okay? And then here show my covariates. Okay, so assessment, highly significant positive. That if they had a good assessment, they had a good satisfaction score. Right? Happiness. So if they were seen by nurses that had higher satisfaction ratings in terms of their job, they also had a more they had higher satisfaction ratings post-operation. Okay? So both of those have positive effects. Okay? All right, this shows the equation here of the multi-membership model. So what's interesting here is, I think, is, we have a random effect for the clustering of the patient within nurses. However, it's being weighted by PIJ, by the weight. How much time did each patient spend with each nurse? Okay? And again, the sum of those weights equals 1 for all patients. And so it's really just a simple two-level model in a sense, except that now, again, each person is not necessarily within just one cluster. They're potentially in many clusters. Okay? Now, if I add in a nurse covariate, as I did, right, what I'm doing essentially is to weight that nurse covariate by those weights as well to get a weighted average. Okay, so this is basically what I just showed in terms of running it with SAS. We did this kind of model. You could write it in this matrix way as well. Okay. Here's how to calculate the interclass correlation for the multi-membership model. Okay. What it tells us is the pairwise correlations of patients, the dependent variable from the patient, within a given cluster. And again, it's always conditional on covariates. So the ICC can be different depending on whether you have covariates in the model or not. Okay. And so these vary here depending on the patient weights. Okay. So, for example, let's say we have two patients that were cared for by the same nurse for the entire hospital stay. So then we would calculate the ICC in the common way. We would put the nurse variance in the numerator, and then the sum of the nurse and residual variance in the denominator, and we say the correlation of the dependent variable, the satisfaction here, is about 23%. Okay? So pretty correlated for patients seen by the same nurse for their entire stay. Now let's say we've got two patients that were cared for by the same nurse, say nurse 2 for half of their stays, but then different nurses for the other half. Okay? So for example, for the one, say they were seen by nurse 5, and then for the other person here, say they were seen by nurse 8. Okay? So then the IC calculation is down below here. The numerator uses both of the 0.5, okay? And then in the denominator, what I have is first the standard deviation, as it were, for the first person who was seen by 2 and 5, and then the standard deviation for the second person who was seen by 2 and 8. Okay? So here we do this calculation and we get an ICC of about 6.5. So you can see here in the multi-membership model, there's many possible ICCs depending on kind of the pattern of who they were seen by. Okay? And this now is where we're going to now get into situations in which the data are both longitudinal and clustered. Now here, my colleague Guy Caffrey, he initiated this paper that we published in Psych Methods in 2015. It's included in the reference section. And I think it's a really good resource for this scenario of longitudinal and clustered. And there's also an accompanying, there's a sort of a supplementary materials that has a lot of the syntax for how to run these analyses. So I learned a lot from Guy about how to do this. He was really the expert here. And Greg Ahrens was also involved in this. So let me show you again what longitudinal and clustered looks like as we compare hierarchical to cross-structured. Okay. All right, so let's say we have a subject 1 who is measured 3 times. Okay, so here the syntax is IJK for observation I nested within subject J within class K. Okay, so this person, subject 1, stayed in the same class for all 3 measurements. And subject 2, likewise, stayed in the same class for all 3 measurements. Now here shows a cross structure idea. Here, subject 1 was in class 1 at first time point, class 2 at the second time point, but then class 4. So they changed classes across time. Subject 2, let's say they were in class 1 in the first time point, and then they moved on to class 3, and they stayed there for the next 2 measurements. So this shows how there can be a crossing between classroom here and subject, right? So here it's strictly hierarchical, here it's crossing. So subjects can be in different classes at different time points. Now, I think this happens all the time in educational research where we measure them longitudinally. Kids don't stay in the same classroom. They don't stay in the same school necessarily across time. Oftentimes what people do though is they'll use maybe the first classroom, the first school that they were in and keep that throughout. Okay, that's not optimal, right? So we're going to show how we can take this into account, the fact that students can change clusters across time. And the first class of models we're going to do here are what are called acute effects cross-classified multi-level models. Okay? So here we have repeated observations within clusters with subjects in potentially different clusters at different time points. So again, they don't have to be in different clusters, but they can be. Okay? And in this case, subjects and clusters again are crossed. Okay? Now, typically in these kinds of models, we might have multiple random subject effects because we might have a random intercept and a time trend. Typically for the clusters, we'll only have random intercepts. What we're going to see is we're going to allow that also potentially to vary across time. Now in the acute effects version, it won't. When we get to the dynamic effects, it will. So the cluster effect here is for a given subject at time point, and it depends on which cluster a subject is in at that particular time point. So here's the data set that a guy analyzed in the paper. It was from early childhood longitudinal study. Here, the outcome is the math achievement, and we have a student gender, and we have the school type. Was it a public or a private school? These are predictor variables, and they're measured at 4 time points: kindergarten, first grade, third grade, fifth grade. And there's a total here of 245 schools. And there's some kids that went to different schools across time. So between kindergarten and first grade, about 5% of the kids changed schools. First and third grade, close to 10. Between third and fifth, again, here 8%. Okay, so not everybody stays in the same school across time. Here's the Excel file that we have here. So here's school child ID. Okay, so that's the 4 repeated measurements. So it's in the long structure here. Their gender. Okay. Here's the school ID according to this cross-classified model that I'm going to be utilizing. So here, this first student, for example, was in the same school for the first 2, but then changed schools for the latter 2. Now here is a dependent variable, their math score, and here also is an ID variable where I would just use their first school. Okay? Now again, that's not optimal because this person changed schools. Okay? But again, that's I think what's perhaps commonly done in these kinds of studies. So what I'm going to show is how we can take into account that the student changed schools. Okay? So here's a listing of these variables in this Excel file. Again, the one we're going to look at is their math achievement, and we're going to use the school ID for the child at each time point. We've got gender, we've got time, and we I think also have whether this is a public or private school. And again, that's a time varying variable because kids can change the school that they're in. Okay? Okay, so this shows SAS syntax for running this acute effects cross-classified model. Here I'm going to identify the child ID and then the school ID on the class statement. And then I'll have here 2 random statements. One for the student, for the child, and here I'm running a random intercept and time model. Okay. Type equals structured allows the intercept and the time trend to be correlated. And here I have the clustering attributable to school ID. It's denoted CCREM because this is the ID that potentially changed across time. Okay. And here in the model statement, I'm modeling their math score in terms of time, the gender, the school type, was it private or public, and then I'm looking if there's a gender by time interaction. Okay, so this is how to do it. You can see it's not that difficult. Let's see what we get. Here shows the residual log likelihood. Here show the covariates. So here's my interpretation. The mean math score, approximately 37, when all the covariates are 0. That would be kindergarten for males in private schools. And you can see here gender and the gender by time interaction, not significant. There's a significant improvement per year by about 15 points. Okay. And the school type, there is an effect such that public schools have lower averages by about 5.5 points. So those are the covariates. Now here are the covariance parameter estimates that we get. Okay. So the first three are for the random effects for the subject. What's listed as on 1,1 is the random intercept. What's listed as on 2,2 is the random time trend. And these are positively correlated. The covariance is 2,1. And then here is the cluster variance attributable to the school the child was in at the particular time point. Okay. Now here, what I also did was I ran a simpler model where I didn't include the cluster in the situation. Well, you can see that if you do a likelihood ratio test, adding the cluster is highly significant. Okay. So there's appreciable clustering of the math schools attributable to the schools. Okay. So in other words, schools vary in terms of higher or lower math scores. Okay. Now, finally, in the time I have remaining, let's get to the dynamic group multi-level models. So far, subjects have been considered either in the same cluster across time, and here sometimes in the paper he used group instead of cluster. I'm here using cluster primarily, or in different clusters at different time points. Now, an implicit assumption in both of these cases is that the cluster effects are the same across time. So in that case, they're perfectly correlated. It's the same, so the school here that we've been considering has the same effect on kindergarten, on first grade, on third grade, on fifth grade. Well, that may not be the case. And Dan Bauer in 2013 published a nice paper in which he described dynamic group multi-level models, which relax this assumption. And they allow different cluster variances across time as well as different correlational structures. Okay. So here there are many structures that are possible. What I'm going to show an application of is the most general, which is what's called unstructured, in which the cluster variance is different across time and all of the correlation parameters are also potentially different. Okay. But if you read Bauer's paper, you can see mention about these other structures that I've listed here. Okay, so here shows the difference between the acute effects, which I've just run, and this dynamic group multi-level model that I want to do. Okay? Now, in the acute effects, I just have a random intercept, okay? And it estimates one variance for the clustering. So it assumes it's the same across time. In the dynamic group multi-level model, what I do, instead of putting random intercept, is I put the time variable as a random effect. Now, in SAS, it wants that to be a class variable. So that's why in this data set, there's a variable called year 2, which is just the same as the year variable. But here, it's going to treat it as a classification variable here when it forms the random effect variance covariance structure. Whereas on the model statement, and on the random subject effect, it's treating it as a linear predictor. Okay. So that's the difference there. So here, year 2 is a duplicate. It needs to be at a class statement because it's here on the random statement to form this dynamic group multi-level model. And here, type equals unstructured. Again, what that's going to do is to say, well, what's the clustering effect at kindergarten? What's the clustering effect at first grade, third grade, fifth grade? Those are all will be different, as will be the covariances between those. Okay, so here first show the covariate effects, the fixed effects, and here's the log likelihood. I'm going to use this in a deviance test in just a moment. Okay? So the interpretations here are rather similar, actually. Okay? They don't necessarily always align in this case, but here they're pretty robust. Okay? Here show all the variance covariance parameter estimates. Okay, so here there's quite a lot because the first three are for the subject: random subject intercept, random intercept trend covariance, random trend variance, and then shows a 4x4 matrix for the school clustering effects. Okay, so what's 1-1 is the clustering effect at kindergarten. So the variance there is 17. At first grade, 2-2, it's 81. It's jumped up a lot. So in terms of, the cluster effect of the school on the math score, it's not that large at kindergarten. It's quite a bit larger at first grade. And then at third grade, drops off a bit, but still pretty big. And at fourth grade, likewise. Okay? So it seems here, in terms of the clustering effect, year one is very important. Okay? Kindergarten, maybe not so much. Year one, very important. And then it's of intermediate size between third and fifth. Now, what I'm going to finally show you, and then I'll stop talking and address questions, is how we can use these variance parameters to get a correlation matrix. Okay? Oh, before I do that, here shows comparing the models. Okay? So this is just about comparing the acute effects and the dynamic effects model. And again, in this case, we want to find out, is it the case that the clustering effect is the same across time, which is what the acute effects model assumes, or relaxing that, is it the case that the clustering effect is different across time? Well, I can do likelihood ratio test here, and you can see that here you get a chi-square value nearly 200 on 9 degrees of freedom. And it's 9 degrees of freedom because of the different number of variance covariance parameters that these two models estimate. Okay? And so what that would do here would reject the acute effects model in favor of this dynamic effects structure. Okay, so finally, here shows a little script using IML, how I can convert a covariance matrix to a correlation matrix. Since I want to get to the questions, I'll just, I'm just inputting the covariance matrix here. And then here's the equation for converting a covariance to a correlation matrix, and then I print that out. And so here show the correlations. Okay. All right, so what you see is that they're pretty strong, as you would suspect, right? But they tend to diminish if the time lag is increased. Okay, so for example, here shows a correlation of kindergarten and fifth grade. Well, that's not quite as strong as kindergarten and first grade, as you would expect. Okay? And the correlation seems, at least within that first lag, to increase a bit across time. Okay? So realize here, again, the acute effects model would say all of these correlations they're equal to 1 because there's only one variance. Here, though, they look quite different, right? So the dynamic model seems to be a better choich here. And again, the chi-square statistic obviously points to that direction. Okay, so here, just to summarize, I went through cross-classified, multi-membership, and then these two kinds of cross-classified longitudinal models, the acute effects, the dynamic effects. And again, what I've illustrated is how to use SAS to do these models. Again, in the appendix, I have some additional software, Stata and also SPSS, how to do them. And SAS also has a kind of an interesting proc called HP mixed that is a little bit more computationally, doesn't take as much time sometimes as proc mix that is potentially useful. Okay. So I think I'll stop here. Again, here show the references that I've made reference to throughout the talk, and happy to answer any questions that there might be if I wasn't crystal clear on what I presented in this workshop. So happy to open the door to questions at this point.
Thank you, Don, very much. Terrific presentation, lots of questions from the audience, and Dr. Moyer and I have included a few as well.
Okay.
We'll start with some general things. So the methods that you've described, you were applying them in all of your examples, I think, to observational data, and certainly they're applicable there.
Mm-hmm.
I tend to work in the world of trials where we randomize participants to study arms, and often I work in group randomized or cluster randomized trials,
right.
Like that. So is there any general guidance that you can provide on when we need to pay attention to something like cross-classification? Do we always need to pay attention to it in observational studies? Are there circumstances in trials where we have to pay attention to it?
Yeah, I think it's really like to my mind at least, it's kind of mimics like when do we have to pay attention to clustering, right? And clearly, if you have a cluster randomized trial, you need to pay attention to it. But I think it's also beneficial to take into account this cross-classified even in the randomized setting, because it's often the case you might randomize, say, schools to different intervention arms, right? But then the kids within those schools might be changing schools, might be in different classrooms. And therefore, it seems to me it's beneficial to incorporate these cross classifications into the analysis, because even in a randomized trial there, they'll presumably eat up some of the variance. And because it's randomized, it should be rather equal across the study arms. And so it seems to me it'll eat up variance, and it won't be necessarily related to the treatment effect of interest. And so you potentially will gain statistical power. So I think it's useful to do these. And the thing is, again, I think it's all rather doable. So, why not do this? So,
Okay.
I think it kind of mimics to me again, early days of multi-level. When do we need to pay attention to this? Well, again, it seems to me rather a lot, I would say.
Is there a downside to ignoring it? So we tend to think of type 1 error rate and
Yeah.
power, and you were
Yeah.
just arguing it, including it might actually help power. There might be situations where ignoring it could inflate the type 1 error rate or hurt power. Can you speak to that?
Yeah, that's a good question and good comment. Of course, now some of the papers I looked at, they basically that I included in the references here, they've looked at those issues by simulation, right? So here, for example, the third one, these here, an evaluation of criteria for correct cross-classified model selection. So what they did was to look, well, what if you have cross-classified, you don't take it into account and just go with hierarchical modeling? What typically you see there is that the standard, the fixed effect, the betas are fine, but the standard errors are not necessarily, because the variance structure is not correctly modeled. And so there, it seems to me, there would be scenarios where there could be type 1 errors, because again, you don't have the variance structure correct. Therefore, the standard errors for your fixed effects aren't exactly right either. So again, it would kind of depend. And what they do often in these kind of simulations is they see, well, if you say have only 5% cross-classified versus 20% cross-classified of the data, right? Obviously, in the latter case, it's going to have more potential for an effect. So it varies a bit also how much of this crossing is going on with the data set. And, so it would seem like that's the first thing to investigate, I think, with a data set is how much crossing do we have? And is it rather trivial, or is it more commonplace than we might suspect?
And would you make similar comments about multiple membership and dynamic group structures? So if they exist and you ignore it, can you get into difficulty, or are you just hurting yourself in terms of power?
Yeah, there was a paper there. Let me see if I can get to it. Which one was it that looked exactly? Yeah, here, this one here. The impact of using incorrect weights with the multi-membership random effect models. So there they did a similar sort of simulation study to look there. I think the thing that if you think about it, again, I think you would get, like let's say there is the case that people are seen by multiple providers, but you only use one of them, right? Again, it seems to me you're going to get the variance estimates not exactly right. And again, it would seem that would then impact the standard errors. And then, depending on whether the covariate is at the cluster level or at the subject level, that would impact either the type 1 or type 2 error, it would seem. So, again, it seems like something that we need to pay more attention to than we have. And again, it doesn't seem to be terribly difficult to do so. So I think it's worth investigating.
You mentioned that one approach to defining weights in a multiple membership model is to base it on how much time the participant spent with that provider, for example, or
Hmm.
with that teacher.
Hmm.
And certainly that's one approach. I've heard multiple membership models criticized because the analyst has to specify weights
Yeah.
and they might not, guess correctly.
Hmm.
Is there a way to test whether the way that you've structured the weights is right, or are there sensitivity analyses that you can do?
Yeah, I think, to my mind at least, I think the sensitivity would be the first thing to do, right? To see, does it matter the way I define the weights in terms of your conclusions? Now, hopefully, when you do that, right, you find out it doesn't matter. So then you have more confidence in your results for sure. But sure, that's the first thing one would do. Now, if it does matter, so let's, then I think you have to think more closely to, well, which way is the better way of defining it? And to my mind, at least, no, that's not purely a statistical decision. Now, you could certainly, these are not nested within each other, it seems to me. So presumably there you could use AIC as a judge of which one, quote, fits better. You couldn't do likelihood ratio test per se, but you could use the AIC as a guide. But also, it would seem to me that substantive thinking, which way makes the most logical sense should also play a role in that decision. But the first thing to do would be, if you have several ways to, to try them all, to do the sensitivity analysis. Then in reporting your results, you can say you did that, and and the results were robust or not, and then go into that in more detail. Okay.
Your presentation has focused on continuous outcomes, but I know you play a lot with other kinds of outcomes. And so can you comment on, are the methods that you've been talking about today equally applicable if you've got a binary outcome or a ordinal outcome or a count outcome?
Yes, thank you. I always like to promote ordinal models because that's where I've spent a lot of my time. Certainly, in all of these cases, in SAS, for example, I've used proc mixed, but all of these things can be embedded within proc glim mix in SAS that would do modeling of binary outcomes, logistic models, say ordinal outcomes, cumulative logit models, could be Poisson outcomes. Now, I will say this, when you go from continuous normal to categorical models, the estimation complexity is increased. So in theory, all of these things translate, but I would think there could be the possibility of a bit more computational demanding in some depending a bit on the data set. So in theory, yes, all of these things do translate, and probably most cases they would, but I could think that there might be some additional computational issues sometimes.
What modifications are required if the clusters differ a good bit in size? So schools are never the same size. Hospitals are never the same size.
Precisely. Well, just like in standard multi-level, there's no assumption that they are the same size. So, there's nothing per se that the likelihood that that's being formed to estimate these parameters acknowledges how much data comes from every single cluster. Now, if you feel that large clusters might have a different outcome than small clusters, maybe you define a covariate in that way and include it in your model as a covariate. But there's nothing intrinsically wrong about having clusters of different sizes whatsoever. Yeah.
Um, if somebody is familiar with the methods, aware that they're likely to encounter this stuff in their study, let's say they're planning a trial,
Mhm.
are there methods available to do sample size calculations that take these things into account?
Yeah, that's a good question. Well, certainly, here's what I would do. You can do simulation, power via simulation. That would be a go-to. I don't know per se that there are, um, you know, papers and programs out there, because it would depend a bit about how much of this cross classification is going on, right? So it would seem like, yeah, that there would be more that one would need to consider in the power calculation. But really, it would seem also like it's, there's methods out there for dealing power calculation for cluster randomized trials, as you know, David, and we've worked on similar things. So it seems like they could be generalized to this scenario. So maybe some people have done work in that area. I don't have a good answer other than resorting to simulation, which you can always do to get power in these more complicated
And
scenarios.
this might be a situation where simulation is the best approach because every situation is going to be different, and writing a program that would accommodate a general case seems like a real challenge.
Yeah, that's what I was thinking. You know, it would be it seemed to be each case is rather unique, so it's hard to come up with one program that would handle that.
Yeah. I'll ask one last question, and then I'll note that there are so many questions from the audience that we have not been able to get to. We may send you a list of questions and invite you, if you're willing, to draft brief answers that we can post on the website, and
Sure.
or you may encourage people to just contact you directly.
Yeah, sure, that's fine. Either way, that's fine. Happy to try to clarify whatever I can. Yeah.
Okay. The last question that I would ask is, you haven't said anything about degrees of freedom particularly. They were shown in your examples,
Hmm.
and SAS has a variety of ways of estimating degrees of freedom, and
Hmm.
there've been a lot of papers on how to calculate degrees of freedom for complicated mixed models. Some
Hmm.
people have argued that Kenward-Roger,
Hmm.
especially their more recent paper, their 2010 paper, is the way to go. Other people have pointed to Satterthwaite. People have been critical of some of the default SAS methods.
Yeah.
Do you have any comments on that?
Yeah, that's a great question too. Well, I think the same issues apply vis-a-vis degrees of freedom, whether they're cross-classified models or just hierarchical multi-level models. So, you know, here the data sets have been rather large that I've analyzed, so it really doesn't matter. But true, if you have scenarios with not so many clusters, then the Kenward-Rogers approach would seem to be a good way to go, and that's all implemented in SAS and Stata. I think SPSS as well, so that would be something to consider. But again, I don't think the issues would be any different necessarily, other than thinking that, well, here the numbers of cross-classified clusters might be small, and then might lead me to do that more often.
Okay, thank you.
Sure.
I want to thank everybody who participated in today's webinar. On the Mind the Gap website, which is prevention.nih.gov/mindthegap, you're going to find several resources for this talk, including the slides and a list of references. We will also post a recording of today's webinar on that website in a few weeks, probably 2 weeks. You will receive an email with a link to the recording as soon as it's available, so you don't have to wonder. I want to thank you and thank Dr. Hedeker very much, and wish everybody a great day.
All right, see you all. Thanks for your attention in the cyber world.